Hello, folks. Today we are going to be learning about metallic and ionic bonds. You should have some the slides in front of you so you can take notes on. Let's jump right in. First, we're going to start a unit all about bonds. The most recent Bond in the James Bond series was Daniel Craig. He is an American, but played a British 007. And I actually liked him as a James Bond, and I'm going to miss him. I think he's going to do maybe one more movie that I've seen. But today, we are learning about a different kind of bond, metallic bonds. And metallic bonds are really important because they are so important for so many materials that we use. One example is copper wire. And without copper wire, we wouldn't have electricity. And the reason why copper wire has the properties that it has, it can be made into wire. Copper can be pulled into wire, and it can conduct electricity, is because of its metallic bonds. I think this video right here does a really great job of explaining it. So let's take a look and watch this video. We actually haven't learned about that yet. So those are the main points about metals. Let's continue on. Okay. So we know that there's a staircase in the periodic table, and everything to the left of this staircase except hydrogen, these are all metals. So what engages in metallic bonding is all of these substances to the left side of the staircase. And let's take a look in detail about how this sea of electrons works. Let's take, for example, sodium, or you know what, better yet, let's take lithium. Lithium, if I were to draw the Bohr diagram, has two valence electrons, or two electrons on its first shell, and then one valence electron on its outer shell. And so what happens is this one valence electron is right here. And if it moves around uh, to another nucleus, it will have a full outer shell and a positive charge. So that is why it doesn't mind letting go of its one valence electron. That is why its one valence electron is free to move around. Because if it does, it has a full outer shell. And so you have an attraction between all of these positives and negatives with these electrons moving around. And we call that a sea of electrons. If we were discussing a group 2 metal, let's say, for example, beryllium, beryllium has 2 on the first level and then 2 on the second level. We see that if its 2 valence electrons move around, it will have a charge of +2 and it will have a full outer shell. So these 2 electrons are free to move around. They are delocalized. And these electrons, as they move around, act as a glue. They move around everywhere. And that's why we call it a sea of electrons. So how are metallic bonds formed? They are formed by delocalized, and I'm going to put a sea of delocalized valence electrons. So a sea means we have a lot of them. Delocalized means they can move around. And we're talking about the valence electrons in particular. What properties do they give metal? Well, they're malleable, they're ductile, and they can conduct electricity. How do they conduct electricity? Well, this is conduct heat and electricity, by the way. Let me give you an example. Let's say this is a wire. The way electric current works is I have electrons, which are these blue dots, that get pushed into a wire from a source of power. And they don't travel through the wire like a tube. What happens is when new electrons come in, an electron down at the other end of the wire pops out. Sometimes you might imagine electricity as traveling really fast, but actually it doesn't travel that fast. Electrons move at a very slow rate, but they transfer energy down the length of the wire really fast. It's kind of like when you have a row of shopping carts and one shopping cart gets pushed into the back and then a shopping cart gets pushed out from the front. The actual shopping carts themselves aren't moving that much, but the shopping carts will pop out down at the end of the row of shopping carts really quickly. It's the same thing with electricity. By the way, metallic bonding also gives metals its shine, so they have a certain luster because of these delocalized electrons. So that's metallic bonding. The next kind of bonding we're going to learn about today is ionic bonds. And we're going to learn about how to draw Lewis structures of ionic bonds. Well, let's take a look. Ionic bonds are when electrons are given and taken. Here we have an example between sodium and chloride. Let me go ahead and draw the Bohr diagram I'm going to draw the Lewis structure of sodium. How many valence electrons does sodium have? It has one electron. How many valence electrons does chlorine have? It has seven valence electrons. If you notice here, chlorine just needs one electron to form a full outer shell 8. So when it comes near chlorine, when chlorine comes near sodium, sodium gives it that one electron that it needs. And then after it does that, chlorine now has a full outer shell. It forms a minus charge, and sodium forms a plus charge. And that's what we see happening here in this animation. And because one is positive and the other is negative, they attract each other because opposite charges attract. Ionic bonds are when electrons are given to each other, they're given and taken. And one way to remember that is ionic kind of sounds like I want it, like a kid in the candy store. I want it, I want it. That's and it kind of reminds you that when it comes to an ionic bond, it literally wants the entire electron. Ionic bonds are about giving and taking. They form positive and negative charges. For that reason, they occur between metals and nonmetals. Let me redraw this staircase. For example, chlorine is a nonmetal, sodium is a metal. They can form an ionic bond. Sodium will form a plus charge, chlorine will form a negative charge. Ionic bonds always form between metals and nonmetals. Real quick, what happens when ionic bonds form is because it's they form positive and minuses, they arrange in a specific structure like this, where positive and negatives repeat. We call this a crystal lattice structure. Because they form this crystal lattice structure, it makes them very brittle. And when we talk about ionic substances or ionic formulas, we're usually talking about the lowest ratio of particles in a substance. So NaCl is right here. It's the lowest unit. We wouldn't say two NAs with two Cls. We would just say NaCl. But we don't often see NaCl by itself. They are always forming a crystal lattice structure. We would never see NaCl by itself, or we would never see CaF2 by itself or Fe2O3. They're always going to be in a crystal lattice structure. These crystal lattice structures are very strong, which is why the boiling points are so high. It takes a lot of energy to break apart this crystal lattice structure for it to melt and to turn into a gas. So it has very high boiling and melting points. For example, sodium chloride's boiling point is 1,413 degrees Celsius. Let's practice drawing some Lewis structures of different ionic substances. This is how we show how electrons are being transferred and which elements have which charges. You should do this on a sheet of paper or on your notes. For NaCl, I know that Na forms a plus charge and Cl forms a negative charge. I'm going to draw the letters and then the charges. And then I'm going to put 8 electrons around the anion, which has a negative charge. By the way, anything that has a negative charge is called an anion. Anything that has a positive charge is called a cation. Let's do MgCl2. When I have 3 elements, I'm going to put whatever I have one of in the middle. And I'm going to have chlorine, the 2 chlorines to the side. And chlorine magnesium originally has 2 valence electrons, but it gives these valence electrons to each chlorine because chlorine has 7 valence electrons. And when it gets 1 valence electron each from magnesium, it will form 8 electrons in a full outer shell. So I have my letters, I put my charges. Magnesium forms a +2, chlorine forms a -1. And in this case, magnesium gave 2 electrons, 1 each to each chlorine. For lithium chloride, I'm going to put my charges. Li has a plus and chlorine forms a -1. Sometimes I'll do minus, sometimes I'll do -1. And I draw my valence electrons around chlorine, just like this. So lithium gave 1 electron to chlorine for it to form a full outer shell. Let's do Li2O. I have 1 O and 2 Li's. What should I put in the middle? I'm going to put O in the middle, and I'm going to put Li on each side. Then I'm going to write my charges. I know O forms a -2 and Li each form a +1 charge. Sorry, my screen keeps skipping ahead. Then I'm going to put 8 electrons around the element with the negative charge, my anion. I do this because oxygen originally had 6, 1, and then after lithium gives 1 electron each to oxygen, oxygen now has 8 electrons and lithium has 0 valence electrons. It has a full shell. So underneath, it does have valence electrons. Each of them have a full shell of 2 valence electrons. But in this picture, they now have 0 valence electrons because they gave them to oxygen. Everything has a full shell now. Let's take a look at MgO, our last one. This is Mg, this is O. I have a +2 charge from magnesium and a -2 charge from oxygen. You could have gotten those from your periodic table. Magnesium will give 2 electrons to oxygen, and oxygen started out with 6 valence electrons, so I'm going to draw 8 valence electrons around my anion. After magnesium gives 2 electrons to oxygen, it forms a full outer shell, and everyone's happy. That's how you draw Lewis structures of ionic substances.